Um, Hello guys. How are you doing? Sorry, I need to make sure that I can hear my voice. I mean, I can hear myself, but I'm not sure if you guys can hear me. So, I need to fix some things real quick. Okay. I think the sound is coming in. All right. It's a great weekend. Um, Once again, we are back to solve some data structures and algorithm questions. Now, today's session, like I said from yesterday, um, is going to be special, right? I said it was going to be special in the sense that I really want to go back to, linked lists, revise everything I know about linked lists so far, right? For the few days remaining to complete this 100 days of data structures and algorithm challenge, I'll be doing that, right? Um, I happen to like linked lists, you know, a little bit more than every other data structure I've seen so far. The reason being that I linked this was actually challenging for me when I was starting out, and then it became um it became a little bit you know I will not say easy because there are still some linked list related questions that I can't solve, but I understand, certain things about linked list now than I used to, right? So, and this has helped me a lot. And I would like to share everything I know with you guys for the rest of the days that, I have left to complete these 100 days. Now, don't get me wrong, this will not make you an expert unless you keep practicing over time and then you become experts with this data structure. That said, right, I would like to check the chat channel. So today I can be answering questions simultaneously, right? Meaning while I'm solving the questions, I can be checking. I usually do that, right? So it's not the first time I'm doing this. So I'll be checking in with you guys and be answering your questions as well. Hello, Ransom. Hello, Uzbek. How are you guys doing? All right. I think um we can get started for now. So today's session is going to be at least over an hour, right? And basically, like since it's a weekend, we'll spend more time on the session on the stream than usual, right? Okay, so I'll put this back here and we can get. All right. Okay, so that's about it. Let's get started. Now, the the most important thing to note about linked lists is that they are used just like arrays, right? They are a replacement or let's say an improved version of arrays. Now they are not exactly arrays. They do not possess the same properties as arrays, but they actually have similar way of they actually have something in common, which means they store, a list of data, right? It's a storage algorithm that helps you store a certain amount of data. Now, how the data is stored in each of these algorithm, right? In the case of arrays and linked lists, is what makes them different, right? Now, I'll erase the board here and use this to make an illustration. Now, you might have come across images of linked lists, right? Where you see circles and then arrows pointing to other circles arranged in a straight line, right? So let's make an illustration of linked list. So let's say we have 1, 2, 3, and 4, right? Let's just put it like this. This is enough. Now, here is a linked list. This is what you'll see, anytime you come across a visual form of a linked list, right? What a linked list looks like. But you see, these values here, right? The 1, 2, 3 you see here are simply integers, right? That were stored in the linked list using specific methods, right? Or using, let's say specific methods. So the values themselves are not directly stored in the linked list, right? So we store them in something called nodes. So here is a node, right? And the node of a linked list has certain properties. We have a node like this. The properties of a node is the value of the node and the next pointer. Now this is initially null, right? And this will be the value of our node. So in this case, let's say 1 here, right? This will be 1 as its value, and the next of this node will be the value 2 here, or the node 2, not the value 2, because the node itself has a value which is 2, right? The thing you see here, right, this circle with the value inside forms the node, and not to forget the arrow itself. So these 3 properties, right, or 2 properties in this case, are what a node is made up of. So we can then illustrate. So I'm just trying to explain the properties of a linked list, right? So you see, 1, 2, 3, 4 are integers, right? They are digits that we stored in a linked list. We can still store them using a different data structure called a list or an array, right? So in this case, we'll have 1, 2, 3, and then 4, like this. This is okay. Now, what makes a linked list different from an array? Well, every item in an array has a position, and we call that an index, right? So the first item in an array can be found at position 0 or index 0, and then 1, 2, and 3. So this is the property of elements in an array, right? This is all we know for now. If we want to access the first element in the array, right, let's call this x. We can simply do this. We can take x at 0, and this will give us 1. X at 2 will give us the value 3. But we don't have indexes when it comes to linked lists, because every item stored in the list is stored as a node. And then to get the value in the list, we have to get the node itself and then get the value property from that node. So in this case, right, if I were looking for the value 2, which is the second item in this list, I can't. So let's say this list L here, let's call this L. I can't do something like this. L at let's say, for example, just the way we access the value 2 here, just the way we could access 2 here by using x at 1, right? We can't do L at 1 here. This is impossible, but because the way we stored items in the linked list is not the same as the way they are stored in arrays, right? Linked lists are essentially objects, right? Or class formed object forms from classes, right? So, and by classes I mean this here is a node class. So, and then we connect the nodes to one another in a chain, and the entire chain itself forms the linked list. So here we can access the second value in the list by saying list at 1 like this. This is impossible. So for us to access the second value in the list, we have to traverse the list, meaning we have to start from the first node all the way to the point where we want to all the way to the point where our value is, our target value. So I'll put L here. Our target value here, this is 2. So we'll start from this point and go all the way to this side, right, where we find 2, and then we print out 2. Okay, now even when we found 2, right, we can't simply say, okay, the list now, the list at, I would not, this is just an example, right? We can't say the list at 2, right? This will not be what we do. When we found 2, right, to print out 2, the value itself, we need to use the property, right? So we'll say the node here, 2 dot value, and this will return 2. So this is the is really the basic difference between a linked list and an array. Now, I'll still give some more examples, but before we do that, let's understand how we'll be able to get to this node, right? What do I mean by traversing the list? What do I mean by traversing the list? Well, traversing the list is simply looking at the next node in the list. And by looking at the next node, I mean the current node or every node in the list has a next property. We know about that. So when we check if the current node has a next property, then that means there is a chance of having a node after it, right? So we can check if this linked list here, right, L, and we say L. So the first node in the list is called the head, right? And the last node in the list is called the tail. So this is the tail here, and this is the head node, right? So for us to traverse this node, right, we need to use the next pointer of every node. So for the head node, right, we'll start here. We'll say, let me bring this back. Sorry. Oh, okay, that was my bad. Sorry. So we can say head here. I'll just transform this into an H. Head dot next, right? This will point to 2, right? This will point to 2, and we can simply print out the node 2 here. And to get the value of this node, we simply say head dot next dot value, right? And we'll get the value 2 from this node. That's how we can traverse the list. And to get to this next node, right, which is where 3 is, you still attach the next to it, right? So you still attach the next to it. We can still do something like this. Head, okay, instead of writing out head, I'll just put H dot next. Now, mind you, H is the node where 1 is, right? The first node in the linked list. So we say H dot next, right? Dot next again. Now, this is not how you do it. You use an iterative approach, which means you have to write a loop to traverse it. But I'm just showing you what the loop would do, on a ground level or on a surface level. So here's what we do. So we take head dot next, then we take the next, right? So in this case, we've reached the third node, right? And then when we do this again, dot next, we'll get to the fourth node, right? And when we do this, head dot next again, now what do you think we'll have here? Well, again, if you look at this, right, this means we are trying to get the next after this node, and this node does not have any other node attached to it, right? So meaning this node points to none or null, whatever it is, it points to nothing. So the next node in this case, right, if we try to get the next node after the fourth node, so this is 2, 3, fourth node, if we try to get the next here, we'll have a value that is equal to none or null. So it means this node here points to nothing. There is no value. So that's one thing we actually need to understand about linked lists. Now, let's continue with the comparison. So the next thing we'll need to compare is how we insert values in the lists, and compare that to how we insert values into an array. So I'll erase the board once again and keep the original inputs that we have here and there. So let's remove this. Now our array here is X. I'll put X is equal to this, and our list, I'll put L is equal to this. Okay, so how do we insert a value into an array? Well, to insert a value into an array, we simply need to use a method, right? And most of the times we have built-in methods that will help us to do that. So for example, in Python, you can use the append method and append the value you want to append to the array. So you can do something like this. You can say x, right? So you can say this x dot, okay, let me just do it straight away from here. X dot append, right? You append, let's say 5 to this array, right? This is a method, and the resulting array here or list will be equal to 1, 2, 3, 4, and 5. This will be your result, right? So in the case of linked list, things are a bit different. We can't directly access the last item in the array. In the list, in the linked list. It's not possible, right? We don't know where the last item is. We don't know whether the list has 1 or 2 items in the list, right? So for us to insert an item into a linked list, we need to traverse the list up until the point where we meet the tail node. And the tail node is usually null, right? Meaning the tail node points to null. The next pointer of that node is null. So, which means inserting values in linked lists will take more time than it does in arrays. So to insert a value in an array, you simply use append and append the value to the array. That's fine. But to insert a value in a linked list, things are a bit different. So you need to first of all traverse the list, right? From the head node, you go from here, you come here, up until the point where there is nothing else after the current node. Now this means this node is the last node, and we can use the next pointer of this node and attach our new value at this point, right? And our new value will also have a null, which means there's still free space available for any insertion that will happen in the future. So insertion of nodes in a linked list will take us O of n time, n being the amount of node in the list. Meanwhile, in arrays, it takes O of 1 time complexity. It is constant, right? It is constant. So why do we use linked list at all? Well, it really has to do with convenience, right? Arrays take a lot of space in memory, right? Meanwhile, lists or linked lists take not a lot of space, but they actually occupy some space, but it is relatively small compared to the space arrays occupy in memory, right? So let me repeat that again. The reason why we use linked lists over arrays is because arrays take a lot of space in memory, right? When you're storing an item in an array, right, the size of your array increases, right, which means you are occupying or you are consuming more space in memory. Meanwhile, in the case of linked lists, you're not doing that, right? It is relatively small, although we are storing each node at a certain location in memory, but you're not taking up in much space as you would when you use arrays, right? So that's one of the reasons to know, right? And I don't think you would want to use a linked list just for a replacement of arrays. In most cases, right, you'll probably do that in a very complex or very critical situations. I've actually not implemented linked lists myself in any of my programs. Let's say I'm building an application and I had to use linked lists. I've not done that yet, but there is a chance I'll do that in the future. But I've not built anything that requires me to use a linked list yet. But you might want to use arrays. But understanding how arrays work compared to linked lists is very crucial when you are dealing with data structures and algorithms, right? So that's really what we need to understand about linked lists and arrays. Now, one last thing is removal of values in an array, right? Now, when we want to remove a value from the end of an array, right, that will take us constant time, right? But if we want to remove a value, let's say at an arbitrary position, if we know the index at which the item is, that will also take a constant time complexity, right? But when it comes to linked lists, things are a bit different. Removal of values is not the same as removal of values in an array. So to remove a value in a linked list, right, you simply need to direct the pointer of the previous node to the next node. So we go over the node. Let's say, for example, we want to delete 3 from this list, right? I'll rewrite the list here. We'll have 1, we'll have 2. Now we want to delete 3. When we get to 2, right, all we need to do is to access the next node or the node after 3, right, which is 4, and we point 2 to that node. So we'll just do 2.next will no longer be 3, but instead it will be 3.next, right? So it will be node at 3.next, which is equal to 4, right? And then 4 points to whatever it points to, 5 and none. So this is how you remove a value in a linked list. Let me just cancel this out so that we are not using the next node. We are not using 3 as our next node. Okay, I even added .next. All right. So, which is also one of the basic stuff we need to understand when it comes to linked list. Now, let's see whether there are any questions for us. So when you come to it will be my guess. All right, no problem. So have you shared the plan for these 100 days? I do not understand your question, but the 100 days are basically a challenge, right? To staying consistent when you're studying. So I was trying to bring along other people that were even studying data structures and algorithm like I was. So as beginners, right? And then we just set a challenge and stick to it, right? Do the full 100 days, which is 3 months, 3 months plus, if you will. So yeah, I think that was it. 100 days won't be enough for you to be ready to go and take a lead code like question for an interview. I'm not sure, unless you already know about data structures and algorithm initially, then that's enough for you to prepare, right, for your interviews. But when you're starting out, I don't think that's enough. In my opinion, lead code is actually very hard. It is unlike anything you've seen before. These questions just hit you. Even though it's an easy question, right, you still need to take your time and understand the question before you start coding. So I think 100 days is essentially to get familiar with the different data structure there is, and that is not even enough for you to know all of them, right? At least linked lists, binary trees, binary search, stacks, queues, and so on, right? You should be able to get all of those in 100 days, right? At least to a basic level or past basic. Okay, so let's say average level understanding, not experts, right? So that is really what the purpose of this 100 days is. So, yeah, in case you're wondering, car, right? I hope I answered your question. All right, so let's continue. Um, let's continue with the next question we have. Um, sorry, not the next question. The next topic we have here. So, okay, let's take a look at how we can create a linked list, how to insert nodes into a list, and other operations as well, right? And we will take a look at the Floyd, cycle finding algorithm as well. Okay, so let's implement a linked list. Let's see how we can create a linked list. Now, I'll put this in revision. Again, you are going to do linked list basics. So I'll say, so this was, okay, the first revision I did on linked lists. I really like linked lists, to be honest. Uh, if if the entire data structure and algorithm thing was like a stack or a language to pick for, just the way we pick languages where we are trying to program, right? If that was the case, I would have chosen linked list because I like linked list a lot. All right, so let's continue. So I'll create links dash list. Um, this will be basics. I'll put basics revision, and this will be 2, the second time I'm revising this. Now I do this to remind myself how many times I've revised something, right? And it is essential for you, or very important for you to revise. You need to, even if the question is a very easy question that you can solve closing your eyes, you still need to repeat them, otherwise you'll forget. Honestly, that's something I realized about Leet code questions. You forget. You always forget. So you still need to keep you know, an eye out for your questions, and make sure, whenever you see a question, or whenever you solve a question, solve it again the following day. Solve it, as long as you can, right? As many times as you can, sorry. As many times as you can, repeat the questions. And this is like an advice to myself as well, right? It's just something I realized. If you don't solve the question again, you will forget. You will forget. No matter how easy the question was, you will forget. So, always code and repeat. So now let's take a look at how we can create a linked list. To create a linked list, we need those little circles, right, called nodes. And what nodes are is basically objects, right? They are objects with some properties. So for us to create the object, we'll need the blueprint for that object. Now this goes back into understanding OOP. So, for you to solve linked list based questions, or for you to understand linked lists, you need to understand object oriented programming, OOP. And not even to a crazy level, right? Not even like, oh, I really know how, reference copying, or, values are copied by reference, all this polymorphism, and encapsulation and so on. You don't need to understand all of that. You just need to know the basics. Know how to instantiate or create an instance of a class, how to create a class itself, which is the blueprint of your class instances, right? And then know how to access properties from the class, know how to create method from the class, and so on. How to work with properties within the class. Those are things you need to understand in order for you to really appreciate linked list, because linked list is simply everything to do with objects and classes. All right. So, is it so important to remember the solution of the problem? Well, you are not actually remembering the solution, right? It is just recognizing the patterns, right? Let's say, for example, you learned how to find the middle of a linked list, right? For the first time you did it, you understand, okay, that's how we find there's the middle node or in a linked list, right? You understand that. But the next time you see it again, right, because you don't have that muscle memory, if you don't practice how to do it, then you might remember how you did it, but you will not know exactly what to do to arrive at the solution, right? So when you solve a question for the first time and you understand the question really well, it's good, right? You know how to solve that question. Good. That's very awesome. But you still need to repeat it again, right? If you don't repeat it, your brain will just tell you, okay, you know, it's not important for me to retain, so let's just forget about this, right? So that's why the repetition is important, and it's even more important when you actually struggled to solve the question in the first place. Because trust me, even though you struggled and found the solution, if you don't repeat the question again, if you don't solve the question again, you'll struggle the next time. I'm not saying you're not going to solve it, but you still struggle to solve the question. All right, so let's get into it. So to start building a linked list, right, we need nodes, and nodes are instances a node class um of a node class. Sorry. So we need to create the node class. I'll call it list node, right? So this will be called list node. And like I said, the nodes of a linked list have two properties. Now, before you start setting a property in a in a in a class, right, you need a constructor function, right? So which means when you instantly instantiate that class, when you create an instance of that class, those values will be automatically available for you to access, right? So you can't do something like that. You can't start creating properties of the class. Let's say, for example, you do this. Let's say you do, let's define, um, okay, let's say example, right? I'll just call this example, which is a function, right? And then you want to say name is equal to, Sam. I'll just put like this, or let's say Tom, okay? And then when you come here, when you create an instance of this class, so this is OOP. This is nothing to do with linked list itself. It's just some basic stuff I want to explain with when it comes to OOP. So I'll create this node here. I'll say list node, right? And I created this. So let's say, for example, I want to print the name, right? Print node dot name. The name is not available for us, right? We don't have the name property from this example, from this list node class. So you need to create a function that when you automatically instantiate the class or create an instance of the class, the properties you would like to access by default are available, right? So which means to access name, now we create our constructor function, right? So this is going to be you use the init method, right? This is different from any function you create in your class. So we'll use the init, and then we'll say self dot name, right, is going to be equal to Tom in this case, right? So when we do this, now you can see our warning is gone. When we run this function, you can see we have Tom, whereby initially we don't have the Tom name, right, in without the constructor function. again, let me just prove that to you. I'll remove the constructor function and then try to print name, and you see we have an error. It says the list node object has no attribute name. So meaning there is no name property unless we instantiate or create on the fly, right? The property we would like to access while creating an instance of the function of the class, sorry. So we'll do this and then we'll have access to our name variable. Okay, so enough of OOP for now. Let's go ahead and implement our node class. So this will have a value. I'll call this value equal to, now when we create a node class, we want to pass it a value, right? So but it is also possible to pass values to instances of a class. You can't just instantiate the class and leave it like that, right? When it comes to nodes, so you need to pass it a value, the value you want to store within that node. So we can say node dot value, right? I'll call this value will be the value here, right? Meaning when we create an instance of this node, so I'll say node here is going to be equal to, sorry, list node, right? Now you can see this requires a parameter, right? This needs to be passed some parameter. So let's say we pass it 5, right? If I print node dot value, then I'll get 5 as my result, which is here. So we do the same thing. So we need the second property of a node class, which is going to be the next. So we need next. Initially next will be none, right? Or null, depending on the programming language you use. So we'll set it to none for now. Now the reason why it's none is because we don't have any. The reason why it's none is because we would use this to add more nodes, you know, next to it, right? So let's say, for example, if we created this node with the 5 value as part of a linked list, to add, you know, a value after 5, it will require us to use this next property, right? So if we say this node here, let's do something. For example, I'll say node dot next, right? And then we set this to another list node, right? And set this to, let's say, 6, right? If we want to see the value after this node where 5 is, we can just say node dot next dot value, and then we'll get 6. So let's print this and see. Now you can see we have 6. All right, so enough of that. Let's go ahead and implement the actual linked list. Now we have the node class or list node class created. We want the list itself. Now what I did here is also, you know, it's also fine to, you know, add node to an existing node to create a linked list. This is all right, but you know, let's say for example you want to insert as many nodes as, let's say for example, I'll call these values, right? Values like this, let's say 1 2 3 4 5 6, right? With that means you have to write node.next equal to this as many times, right, as this one here, which is not really convenient. This is not good. So what we need to do instead is to create a method that iterates over the values and creates a node for each one of those values and inserts them or forms a list with those values or those nodes. So we can do something like this. So we can create here, we can say define. Okay, no, we don't you know, add the method as part of the list node, the list node class. We need to create a separate class for this. So we'll say class linked list, right? And we do this. So again, we'll need a constructor function def init self. Now for this constructor function, right, we will need a a a single or just one property, right? We need to access one property, which is the head of the list. Now remember very well when I was explaining here, I said the first item in the list is usually called the head node, right? This is the head node, which is the first item in the list. So for us to access the entire list, right, we need to always start from the head node, which is a very important property of the linked list class. So we can create here, we can say self dot head, right, and set this to none. Now the reason why this is none is because initially there will be no node in the tree. Sorry, no node in the linked lists. I said tree because they are quite similar, but sorry, that was a mistake. So initially there will be no node in the list, and we'll have the head node as none. Then we will now define a function to insert nodes or to attach nodes in the sequence in order for us to create a linked list. So here we'll have define insert insert nodes. Okay, this is a function and we'll pass it the self parameter. All right, insert. Okay, so all we need to do here is to write a couple of logics in order for us to insert a node in the list. So first of all, we need to create a node with the value. Now when we are inserting nodes into a list, we want to pass this method a value, right? Now the reason why we pass this a value is because we will automatically create the list node once the value is passed into the insert node function. So you don't need to create the list node outside of the linked list class and then insert that node into the list. You will not need to do that. All we need to do here is to automatically create the list for you. So here we'll call this new node, and we'll set this to list node. List node, and this will be passed again. Remember, when we create an instance of our list node, we pass it what? A value. So that value that was passed here during insertion will be passed down to the list node here. So we'll pass it the value, right? And then now the insertion of the node will now begin. So for the first time, right, the first node we insert in the list will be our root or our head node. I keep saying root, and this is really because of binary trees. Anyways, the terminologies are actually similar, so don't be really confused about what I'm saying. All right, so we'll create a new node, right, and then we'll determine if the head node of this list that we just instantiated is null or not, right? If it is null, then the node we just created becomes the head node of that list. So we'll say if not self dot head, right? Self dot head initially will be none. So if we say if not none, if not false, right? Not false is true, right? So we say if not null, which is true, then we'll just do self dot head, right, equals to the new node, and then we return here. Now the reason why we need to return is to prevent any further program here to run. So meaning we added this value here as the first node in our list, and then we wait for the next value before we insert it as the next value in the list. Now how do we insert the next value in the list? Well, we need to traverse the list up to the point where the current node or the last node in the list is the tail node. So we say current node. I usually like using current node, so let's stick to that. Current node will be self.head, right? Self.head, and then we'll see while current node is not null, right? While current node is not null, in other words, while current node, right? This means while this is true, while this is a truthy value, then do this. So we can say current node, right, is going to be equal to current node dot next. Sorry, dot next. All right. So meaning we are setting current node to the next node up until the point where the node, the current node here, right, has a next value of null, right, which means this is going to be a falsy value. So the next time we iterate, right, this here will fail. So meaning the code after the while loop will run at that point. So here's what we need to do. So we can say here after that, we can say current node dot next is now equal to our new node that we created here. Now let's visualize this a little bit and see what's happening. So I'll come here, right, scroll down a little, and then say, for example, we create an instance of our list, right? So I'll just say L is equal to nothing, or let's say, for example, we created the first, so let's say this part of the we created an instance of our linked list class, right? We set the first node in the tree. In the list. We set the first node in the list. Sorry, I keep saying tree. I don't know why. Let me take it. Sorry. This tree and linked list thing is really messy with me because they are basically similar. The terminologies are all the same. Anyways, let's continue. So we have after setting the head of our list, right, we stop any program from running, which is why we returned here. Now the next time when we create another list, so say for example we added 1 as our list, as our first node in the list, so this is head, then 1 here has a null value, right? Or let's take this a little back, right? Say for example, right, this line of the code runs. We created an instance of our linked list class, okay, and then this part of the code runs, and we want to insert 3 as our first value in the list. Now when the list was created, right, the list was empty. All of this is an empty space. There's nothing there. So we created a node, right, with the value 3 in it, and this node here has a null value as the next value in the for that particular node. So when we set this node as the head of our list, right, let's remove this line here, as the head of our list, then we add this node to the list, right, like this, and then it's going to be like this at first. Okay, it's going to be like this at first. Now this part of the code would then run when we try to insert a new node into the tree, into the list. So so we have another node. I'll call this say 7, right, and this will also have its null property as well with it. So here's where things become interesting. Now when we want to insert the second node into the list, we first of all set a current node, which is going to be the head, right, and then we say while current node, which is true, while there is a value for this head, right, this is our current node, while current node is not null, right, set current node to the next node after 3, meaning we are going to set current node to the next, so meaning we just move current node to this point here. Now current node now points to null, which means this loop here will no longer continue, right? We've seen a null value already. We've seen the tail node already. So there is space for us to insert our new node that we are trying to insert into the list. So, sorry. Okay. All right. So all we need to do here is when the second iteration is trying to run, this will fail, right? And then we'll simply set the current node dot value, right? Current node dot next, sorry, will be our new node. So here current node dot next is this node, right? Is here. It's at this position here, right? So this is this. So we'll replace this with the new node we created, which is 7. So this will be equal to something like this. Sorry, I'll erase this part, and then we'll drag 7 from here and bring it down to this place. When we try to insert another node again, so this is a visualization of how the insertion works. So when we try to insert another value, let's say for example we try to insert a 4, right? 4 will also have its own property null, and what we'll do is we'll start from this point, right? We'll check if the current linked list has a head node, right? Yes, of course it has a head node. Now we'll check the next node after the head, right? This is a value, so we set current node at this point, and then we check. Now our current node is now at the node where 7 is the value, right? So we set current node to the next node after this node were here, right? Now current node here is going to be null, right? It's going to be null. So in this case we don't set it yet, and then we'll just take this current node, which is 7, right, and set its next value to the new node we are trying to insert. So here this will be, so we'll first remove this part, and then we take this here and put it here. So that's how, insertion of nodes are made in a list, in a linked list to be specific. And yeah, so we have done that. Now let's print our list to see what's inside. But before we do that, let's try using this linked list, right, and inserting the values in the list to see what happens. If we have an error, then we'll be able to detect what went wrong. Otherwise it means our list is good to go, and then we'll just print the values out. So we can say for value in values, right, for value in values, we can take this, we can say let's first of all create an instance of our linked list. So I'll say my list is going to be equal to linked list like this, and then we'll say my list dot insert nodes, and then to insert node we take a single parameter value, right, and do this. So this is going to be value like this from the loop, and let's do this like this. So run. Now we have an error, which means we need to solve that error quickly. So let's say here, what's the error saying? Sorry, I didn't read it. So none type has no attributes next. All right, so we said while current node. Okay, so this new node here should be equal to, no, hold on, while current node is not null, right, current node should be current node dot next, and then current node dot next should be equal to new node. So what's going on here? So it says non type has no attributes of next. Interesting. So let's see what could have gone wrong here. Again, you see why you need to repeat. Let's bring this back. Let me quickly check here to see what I did wrong. Okay, let's take a look. So, oh, you see, this is my mistake. I see why this is not working. So I'm checking for the current node instead of checking if the current node has a next value, right? So to insert values in a list, right, you need to do this current node dot next. Current node dot next. If the current node has a next value, right, set the current node to the next node. Okay, so that's my fault. I'll take full responsibility of that. Let's run this again. Right now there is no more errors. So again, the insertion will be done this way, right? We'll need to check if this node, right, if the, so let's say we traveled from here to here and then to here, right? We need to check if this node has a next value, right? Or if a node is at the next side of this current node here. If there is a node, then we can continue setting the current node to the next node. Otherwise, if there is no next value here, right, it means the new node we created, right, with the value, let's say for example this will have value 5 and it will have its own null value, right? We'll insert that node at this position here. Okay, so I think that's clear now. Sorry for the little misunderstanding. Okay, so we do that, and yeah, so our code runs just fine. So the next thing to do is to print out the nodes. So let's write a print function. I'll write it as part of the class. So we'll say define print nodes like this. Now this is just going to be straightforward, right? So we'll say we'll define the function, right? The function does not need any parameter. So we'll say current node is going to be equal to the head node, right? So self dot head, and then we'll say while current node is not null, right? While the current node is not null, then we can say current node. So we print the values, right? So we say print current node dot value, right? Is it val or value? Okay, it's value. So current node dot value. Okay, and let's just put some arrows in between, right, to indicate, or to just simulate what we normally see as linked list. And then we say current node dot next, right? So we say current node should be equal to current node dot next. Okay, so let's print this list. I'll call this, okay, let's remove this part here. We don't need this really. So say print, oh sorry, my list dot print nodes, and then let's run this and see. Now you can see we have 1, 2, 3, 4, 5, and 6 all connected in a line, right? So yeah, that's about it really. And what else do we need? Nothing else. If you, by the time we get to, if I print the current node, right, at the end of this iteration, you'll notice it should be none, right? So let's print current node, which means we traveled the entire list up until the end of the list, right? Up to the end, sorry, up to the end of the list. So current node dot value like this, and you see we'll have hold on, or let's just print the current node instead. Now you can see we have none at the end, right? We have none here, so meaning the last node we reached here was none. All right, so that was quite exciting. Let's move on to the next topic, right? We've looked at is creating a list, inserting nodes into a list. We also saw printing a list, or nodes of a list, right? Now we want to find the middle of a list, the middle of a linked list. So how do we do that? We'll write all the functions here, right? So I will commit this one after the other. So I'll say git add git commit this is a linked list, right? Linked list, and this is creating nodes, inserting nodes, and printing, creating, inserting, and printing nodes, creating, inserting, and printing nodes. All right, so that's going to be the first one we did. Now the second thing we'll do here is getting the middle of a list, the middle node, right? So in this case, the middle here is going to be 3, right? Okay, so let's say we have 2 halves, right? Yeah, I mean, when we divide this into 2, right? So for an even number, right, for an even number of items, the middle is going to have 2 values, right? So in this case, if we're to get the middle value here, we'll have to choose either 3 or 4, right? But if we have an odd number of items, right, then that would be easy. Let's say, for example, we have 5 items in this array, then the middle value here is going to be 3, okay? But when we have this here like this, well, we'll have to choose which one is our middle by ourselves. It's either we decide 3 is going to be the middle or 4 is going to be the middle. Okay, so let me quickly, my room is getting dark. I think it's about to rain. Okay, so we are going to check how to get the middle of a linked list, right? Oh, the time is almost up. Wow, that was really quick. Oh, I can't even finish everything today. Wow. You know what? There's no need for that. Let's add 30 more minutes. 30. You know what? 40 minutes is good. Let's use 40 minutes. Cancel, close. All right. We've added 40 minutes to continue the stream. Keep the stream running. Keep the stream running. All right. So how do we get the middle value of a linked list, right? Well, for us to do that, right, there are two ways, and I'm going to show you those methods, right? We have the iterative approach, which means we have to traverse the list up until the point where we get to the middle of the list, or we simply use the fast and slow pointer method, right? So the first iterative approach is going to get us the length of the lists, and then we'll then iterate a second time up until the half of that length that we got in the first place. All right, so we'll take a look at both methods. I think I have some comments here. Hello, Raj. Welcome to um, the data structure and algorithm stream. It's nice to have you here today. So, all right, I trust you're doing well. All right, so let's keep going. Let's keep going. Um, so let's take a look at the methods to get the middle of the linked list. I think what I should do today is to cover, all of these, and then let you guys revise this session, or rewatch this video to understand everything in it. This will basically help you understand linked list, right? I promise you that once you watch this video and you follow the steps or the methods I show in this video, you'll be able to understand linked list, at least past the understanding you had of linked list if you're a beginner, right? Previously, the old understanding you have of a linked list will be blown away, will be surpassed, go from this level high. All right, so again, so I'll cover the basics of linked lists, right? All these different methods today, and tomorrow, right, we'll solve some Leet code questions. Now, with the way I arrange these questions, right, these questions build on top of each other, which also means that if you're able to solve the first one, you should be able to solve the second one. Now, I'm not saying it's going to be easy, but you come up with a solution that is at least working or close to working. Or you just have that solution where you're struggling a bit, and then you see the code and you're like, oh, that's what I actually was struggling with. This is the piece I was missing. So again, take good notes in this video so that you understand what linked list really is. We're going to do all of the methods I know so far. So here we saw how to create a linked list, how to insert nodes in a list, how to print a linked list. Now the next thing is we are going to look at the two different methods of getting the middle node of a list. Now, let's take a look at an illustration here. I'll come here. This is my board, right? Let me adjust this list a little. Okay. All right. That wasn't what I was trying to do. So let's say we had another value here. Okay, we needed a blue color. This is 5, right? Okay. It doesn't matter. Let's leave it as 3. This is still good. Let's say we want to use the iterative approach to get the middle of the list, right? Now we don't have indexes in a linked list, right? So this is not going to be straightforward with the way, or compared to the way it is done in arrays, right? So let's say, for example, we have an array of values. Let's come here, right? I'll copy these values here. I'll go to the playground, which is a file that I usually use to explain, little stuffs. So again, all right. So let's say, for example, right, let me see, what's this one in about? cheeky. Anyway, so that's our array, and then we want to get the middle value of this array, the mid value of this array. Well, it's either you determine the length of the array and divide it by 2 and then just access the value at that point, right? So you can do something like this: values at length of values, okay, and then you divide this and round the value as well. Divide this to 2. So I'll say print this like this. You can see we have 4. 4 was chosen as our middle value. Now this is good. This is arrays, right? But if you notice something, we had to use the length method on this array, and then quickly access that value at that point. This is going to take O of 1 complexity, or O of 1 time complexity, and space complexity as well, because we are not creating any more memory in space. We are simply accessing that value straight away. But with linked list, things are a bit different. We don't know the length of our linked list. We can't even tell the length of our linked list straight away, just like we do it in arrays, right? When it comes to arrays. So what we need to do now is to determine or find the length of our linked list. And how do we do that? Well, we can simply iterate the list or traverse the list, right, up until the point where we meet the tail node, and then we'll find the we'll count, right? Every time we iterate or traverse the list, we'll count. We'll keep track of a count, right? And then once we reach the tail node, the count value will be updated, and that will be the length of our list. So let's take a look at an example here, right? I'll close this quickly. So we take this, for example, let's say print node. Print node traverses the list, right? So I'll say, for example, let's do this. I'll rewrite the function. I'll say def find middle node, right? I'll just call this find middle node. Okay, and what we'll do is we'll say we'll just traverse the list just the way we did it here, right? I'll just copy this part, except that we are not printing anything, so this is a bit different. Okay, we are not going to print, we are not printing anything, but what we'll need to do here is to keep track of the count. So we'll say count here is going to be equal to, now what we in the case of arrays, right, counting is done from 0, right? It begins from 0, so we start counting values in an array from 0 all the way to the length of the array minus 1. So let me show you what I meant by that. So if we come here, right, let's say we print these values and their indexes. So say for I as I can call this value, and then I put index, right? Okay, so it's index before values. Let's say index, and then value, right? And then values in enumerate values, right? We can say print, oh come on, print here. We can do this like this. We can say the value here at index I think, yeah. So the value okay, let's say this is at index, come on, is at index. So let's do it this way, right? We can print this, and you can see we have 1 at index 0, 2 at index 1, 3 at index 2, and so on, right? So in arrays, we start counting values, or we start counting from 0, right? Meanwhile, in linked list, there are no indexes, right? There are no indexes, unlike the ones we have in arrays. So we need to determine where we want to start counting from. And I prefer starting from 1 when it comes to linked list, just because linked list, we can't say the zeroth zeroth node, or the node at position 0 in the list is so node, right? We can't just do that. I think what we need to do instead is say the first node in the list. We can't say the 0th node in the list. We say first node, so which means 1, right? We start counting the nodes from 1. So I will do that instead of using the conventional count from 0, right? So let's do it this way. So we'll start our count from 0, right? And then increment it every time we run the iteration, the loop, right? So say count plus equal 1. Okay, let's return the count and print, or let's just print the count for us to see what we have here. So print count, right, to see how many items we have in our list. Now the items the amount of items we have in the list will also be equal to the length of the values here. So let's print the length of the values here to show you what it really means, what it really is. Sorry. So length of values, right, this will be equal to, I think, 6. So you can see we have 6 here. So item at index 5 or position 5 is 6, but we have 6 values in the array. So 6 node in our linked list, which is why I'm using 1 as my starting position or my counting position. So I'm going to start with 1 and then go upwards. So let's do that here. I'll take this, so we print 1, right? And let's say, for example, my list print node. Okay, we are printing the nodes here. I don't need to print nodes anymore, right? I just need to see how many items I have in my list, which is the count. So I'll say my list dot find middle node. Now the reason why I'm using this function, because we are going to complete it later on, but we just want to see how many nodes we've counted so far. So we can do this, and you can see we have 6, which means we have 6 nodes in the list. So what do we do next? Well, we need to find the middle of this list, which is going to be 6 divided by 2, and then we count again, right? We count again up until that point, and then we determine which node is at the middle. Now mind you, when we printed the middle value here, right, the middle value here, we got 4, right? Let's print this again, 4, which means if we're going to print the middle value of our node here, we have to have 4 as the middle value. So, or the middle node, sorry. So we can do this. So we determine the node. So all we need to do now is to say, we can just say while, or we use a for loops. So let's say for okay, let's create a middle node variable here. I'll say middle node, or let's say middle underscore node is going to be equal to none at first, and then we say for, because we don't need any index here, so we'll say for dash in range of values. So we start counting from 1, right? So say 1 up to uh the middle size, right? The half of the size of the entire list. So we'll say count divided by 2, right? Up onto count divided by 2. So we need to do the double sign division. Yeah. So here we can just reset middle node every time, right? So we say middle node is going to be equal to it's going to be equal to, okay, so first of all we need to say this. We need to do middle node is going to be the head node. Let's start from the head, right? Okay, we do self dot head, right? And then we'll say middle node is equal to middle node dot next, middle node dot next, like this. And then in the end we'll print middle node and see middle node like this. All right, so let's run this again. Now you can see it's just giving us the location of that node in memory. Let's print the middle node dot value like this. And you can see we have 3 instead of 4. Interesting. If you want 4 to be your middle, right? I mean, like I said, for an even length even length or even sized linked list, we will have 2 values at the middle, right? So whichever one we decide is going to be our middle is up to us, right? We can, if you want 4 to be our middle, right, we can simply do this. We can say divide this, right, plus 1, right? The division will be done before the addition, so there is no need for that. Now you can see we have 4 as our value. All right, so this is one of the interesting things. Instead of printing out, we can also return the value, right? So we can say return middle node dot value. Okay, so the next thing we need to do is to look at the second method, which is the fast and slow pointer, and it's also called the sorry, let me see the name again. The Floyd cycle finding algorithm. That's a mouthful. Anyways, so the Floyd cycle finding algorithm is an algorithm where we use to find the midpoint quickly, right, by using a fast and slow pointer. So it involves using pointers, which is fast and slow, right? So with the fast and slow pointers, the fast pointer will move twice as the slow pointer, and by the time the fast pointer reaches the tail node of the list, the slow pointer would have arrived at the middle. So that way we have a very efficient way to determining the middle of the list, right? And instead of us to, decide like this whether it's going to be the next one when it's an even length list, or or just the half, right, node at this point, it doesn't really matter, right? So we need to use, I mean, I'm not supposed to say it doesn't matter, because it actually matters, because now we are in an undecisive state, right? We don't know which one we should use. Is it going to be the first one we see when we have an even length node, or is it the second one, right? And by second one I mean the node, right? So for us to do this, then we need to determine we need to use the fast and slow pointer method, right? Sorry guys, I'm coming. So we are going to use the fast and slow pointer method. Now let me explain how the fast and slow pointer method works. So with the fast and slow pointer method, right, it's actually quite easy, right? So once you see it, you'll be really excited to use it. So let's take a look. So here we have our linked list, right? And all we need to do is to start both pointers at the same position. So we start the fast pointer here. Okay, let's use a different color. We start the fast pointer here like this. Okay, and the slow pointer is going to be at this position. All right, so we move the fast pointer, sorry, 2 steps faster than the slow pointer. So when we move 1, 2, right, then we move this one 1, and the condition for us to continue moving is if the fast pointer has a next value, right? So if there is a node after the current node at which the fast pointer is, then we'll be able to move the fast pointer forward. Otherwise, we won't be able to do it. So in this case, we can simply return the node where slow appeared, and this will be our middle point. Now let's solve the case with the even sized linked list, right? So let's say even size or even length linked list. So let's say we had a linked list like this one. You know what, I don't need to always try put that circle because it's not really perfect. So 1, 2, 3, 4, 5, and 6. So if we use the fast and slow pointers, right, this will basically, settle the debate about which node should be the first node to return when we have an even size linked list. So we'll start the fast and slow pointers here, right? So we'll have something like this. Let's go up a little. Okay. All right, my sis is quite fantastic. Let me. It's too handsome or beautiful. Okay. All right, so we have our fast pointer here. Okay, and the slow pointer is here. So we said we move this fast pointer twice as fast as the slow pointer, right? So we move this from here 1, 2, right? And the slow pointer will move 1. Then we do the same thing. The next iteration will have 1, 2, slow pointer moves once. And since this still has a next pointer, we can do 1 and then it's null now, right? So 2 is going to point to null because 6 has a next value that is null. So this is going to be null. So our fast pointer is at null. And by the time we move it to here, we have to move the slow pointer as well. So our slow pointer is going to be at this position here, which is 4. So meaning 4 will be our middle. So the debate is settled, right? So we found 4 as the middle value of our list, which this the array method also stated, right? 4 should be the middle, not 3. So yeah, let's implement the fast and slow pointer method, right? So I'll say define middle of a list. I'll bring this up here. Middle, okay. Middle of list, right, is going to be a function, and we need to create the fast and slow pointers, right? So fast and slow pointers fast is going to be the head, so self.head, and slow is going to be the head as well, so self.head. All right. And we begin to iterate. Now, our iteration has to be based on a specific condition. As long as there's the first node is not null, right, or the first pointer is not pointed to null, and there is a node after the first pointer, then we can continue, shifting both pointers forward. And the slow node will finally point to the middle value that we are looking for. So here's what we need to do. We say while fast, and while fast means while fast is not known, and fast dot next common fast dot next, right, is also not null, right? We can say fast should be equal to fast dot next, and then slow is going to be equal to slow dot next. Sorry. And that's all we need to do. And at the end, we just return the slow node. Now I'll just return slow dot value, right? So that we see. Okay, let's return slow first before printing out the value. So this will be find middle node. I will just uncomment that, and let's in my list dot middle of list, right? Middle of the list, and we run this. Nothing is printed because we are not printing anything out. So instead of doing that, I will just print the slow node. So print slow dot value. Okay, and you can see 4 is our middle node's value. Okay, so let's commit this as well. Now the next thing we'll look at is reversing a linked list, right? So reversing a linked list is actually really fun and important to understand, because there are a lot of Leet code questions that are, revolving around that. So keep an eye, just be watching your back when the question comes. So git add, let's do this, git commit -m. This is linked list, and this is middle node of a linked list. All right, so let's see how we can reverse a linked list. So to reverse a linked list, the technique is actually quite I won't you have to be careful when you are reversing a linked list. That's all I wanted to say. But I was just looking for a single word to say that. So first of all, the steps, once you memorize the steps, you'll be able to do this pretty quickly. So what you need to note is reversing means the head node becomes the tail node. So for example, right, this is a very long list. Let me remove this part and use my simple list instead. I want to use this list. So say for example, we want to reverse this list, right? So the reversed version of this list will be, 4 to 7 to 3, and then the tail node usually points to what? To null, right? So we'll say here, null. Now you can see 3 becomes our tail node. So how do we do this? Well, First of all, we need two variables to be created at first. So we need a variable to keep track of the current node and a previous node value. So initially, we set previous to null, right? Or none in your case. So let's just use null. So we say current node, or I'll just say cn. Current node is going to be our head node, right? The head of this linked list. So I'll say list.head, right? This is going to be also equal to the node with the value 3 in it. So we say we begin iterating, right? We begin saying, okay, while we have a current node, which means while the current node has a value here, here this is 3. Then we say current node, so we say while current node has a value, right? We need a temporary variable to keep track of every value on the next hand side of the current node. So current node dot next will be every node from this point forward. So from 7 all the way to 4, right? Or even 4 with its null value. So we can just do this from here to here. So those are the nodes after, let me use a different color. Those are the nodes after 3. So we say our temporary value is going to be equal to, let's use this color here. We say temp is going to be equal to the current node dot next. Now temp will keep track of the current node next. Now the next value of this node will now become the previous, which is null. And when you look at the reverse version, you can see the node which is at this position 3, right, has the next value set to what? To null, right? So the next value of this node would then become null. So we just take this, right? We'll say current node dot next. Then we'll say the current node now dot next will no longer be what it used to be, which is, you know, from 7 all the way down here. It will now become previous, and previous was initially null. So we set previous here. Okay. And the next thing to do is to then change previous to become the current node. So previous will become current node. Now by this point, at this time, right, current node is now 3 pointing to null. You can begin to see how the pattern is building up, right? So previous node is that, and then we set the current node now. Current node should become the temporary node we set here. So we set temp, and voila, that's all we need to do. And then we reverse the list just like that. So we'll go into the code and so one last thing, right? Since previous keeps track of the remaining values, right, the reverse version will return previous instead. We return prev. So let's define the function and not run out of time, because we have just 5 minutes left. So we can say define reverse list, right? And we don't need any value, so we need to take current node. I usually like using current node. So current node dot so it's going to be self.head, the head node of our current list, and we take previous and we set previous to be the current, to be none, right? And then we say while there is a current node, while current node, right, while current node, and this means while current node is not null, we need a temporary node, or we can even call this the next node. So this is going to be equal to current node dot next, and we set current node dot next to the previous node, previous node would then become current node, right? And then current node is changed to our temporary node. Okay, and then at the end we can just return the previous node. Okay, so we'll run this function before you know what, I would have run this outside and printed this out, but we can still do it here, right? Before we do any printing of this node, we'll modify the node, right? So we'll say we'll modify the list. Sorry, my list dot reverse the list. Okay, and then print the list. So we'll print the list first of all before reversing it, right? So I'll say print list. I'll copy this part here, paste it. We'll see the original form of the list and then the reverse form of it. So print list and then print it here again. So I'll print here and say reversed version of the list. I think this should work. So let's run this again. Now you can see we have 1 to none. Okay, so meaning something is not happening. Let's see. You know what? It's the returned list here that was changed. So previous has to be printed separately. This is a node on its own. So what do we do in this case? Well, I'm thinking. Okay, let's say we set the self.head to be previous, right? So let's say self.head should be equal to previous. Okay, how about that? All right, now we have the reverse version of the list. Okay, so here is our solution, how to reverse a linked list, right? So we've seen a couple of things today. Tomorrow we'll continue with the rest. Luckily we were in time. We finished on time, right? So we looked at how to create a linked list, how to insert nodes in a list, how to print the nodes of a linked list, how to find the middle node of the list, and we used an iterative approach and the 2-pointer method as well. And we also looked at this is also part of the methods we use to find the middle node of a list, the Floyd cycle finding algorithm. And then we looked at reversing a linked list. So tomorrow we'll continue with the rest part of the questions, or the learning topics, right? So I'll push this to GitHub so you can have access to it as well. So git add git commit -m. You know what? Let's just do this. Reverse a linked list. All right. So git push origin main. Okay, so that's it for today, and thank you guys for watching, and I will see you guys again tomorrow. So there are no questions. I think everyone is pretty satisfied with the explanations. So again, my dear friends on the internet,